Let me start by using this example as the starting point of our study. Let's say we use the matrix displacement method by programming into the computer. However, before you can programming it, you got to do it manually. And I would like to say there is two things in this name. One, matrix. I don't know how much knowledge do you have about this matrix, but you got to be able to use your calculator to do the matrix operation. What kind of matrix operation you got to be able to? One is going to be the multiplication. Another one is going to be plus, minus, and the inverse of the matrix. Okay, you may ask Peoria to help you on this operation of the calculator. But anyway, it depends on the calculator you are using. And the second one, in this method, is called the displacement method. That means we are going to use the degree of freedom of the task to be the unknown. And for the task, one node of the task will have 2 degrees of freedom. For example, we have node A, node 1, node 2, node 3, and node 4. When we have the node, we have the number and the circle. Okay, and if we have the number and the square, that is going to be the member of the task. Okay, and for the degree of freedom, they are important for you guys to know that it's separated into two. One is going to be the constraint degree of freedom. You can see the constraint degree of freedom at the subport of the task. For example, the degree of freedom at node 2, at node 3, at node 4, they are going to be the constrained degree of freedom. And another one, we have the unconstrained degree of freedom, or you may call it the free degree of freedom. Is free to move, okay? And that's going to occur in the node that not the support, such as this node, number 1, okay? And then that is important thing, the number of unconstrained degree of freedom will come before the constant degree of freedom. Okay, based on this, that's why we have this degree of freedom, number 1, okay, in the x direction, and number 2 in the y direction is come before the degree of freedom, number 3, number 4, number 5, number 6, number 7, and number 8. And you can see we have total of 4 nodes. That's why we have the total of 8 degree of freedom, and separate into 2 unconstrained degree of freedom and 6 constrained degree of freedom. Now, when you analyze the task, you got to analyze for what? Analyze for the unknown displacement. So the first step, you got to find the unknown displacement. And the second one, you will find the what? The reactions. Okay? And when you finish find the reaction, later you find the force in each task member. So this is the main step. Number 3, this is going to be the main step. Number 2, and this is going to be the main step. Number 1. Okay? And what is the degree of freedom? That is the unconstrained degree of freedom that you are looking for. That means you're looking to find D1 and D2 for this example. The task on this problem is it has or the member has AE equal to 120,000. Okay, that is going to be the area of meter square times the modulus of elasticity is kilonewton per meter square. That is the unit is in this form. And then this truss at node number 2, okay, number 2 has 1 millimeter downward segment. Okay, that means it's going to have this kind of movement from this green to this black one. Okay, so let's start. We have a lot of things to set up. First thing, we're talking about the global coordinate system. Okay, that means we are going to talking about the coordinate x and y. When we set up the global coordinate system, for example, we set at the node number 1. Okay, and then you will know the coordinate at that point gonna be 0, 0. Okay, node number 1 at the 0, 0. By inputting this into the computer, you mark it node number 1 and then you drag your mouse until you reach your second point, and then this is going to be the node number 2, and then the computer will acknowledge that you putting this one as the member number 1 and you putting this one with the local coordinate in this direction. So this is going to be the near end and this is going to be the far end of the member number 1. Okay, so you got the node and you got the member number and you also get the local coordinate system. Now for the second one, you may mark it like this and then you drag the line from 1 to node number 3 and then you release the mouse. Okay, the computer knows this is going to be the second one. This is going to be the second member with the node of 1, 2, 3. Okay, and then the direction of this member by the local coordinate x half, y half, gonna follow the direction here. And the last one, you may put your mouse over here and you drag the line across this, unleashing the node number 4. You release your mouse and then the computer recognizes this to be the member number 3 with the local coordinate in this direction. And then they know the coordinate of each point by putting the mark on the software. And then it's going to be what? By number 3, you go in this direction, it's going to be minus 1.2. And then you go up, it's going to be plus 1.2 also. For the node number 3, it's going to be only 1.20. Okay, and the last one is going to be minus 1.2, and you go downward for 0.9. It's going for minus 0.9. Okay, that is all going to come by what? By the computer. And the last one, the degree of freedom number, is going to follow what I has lectured you before. It's going to be 1, 2 for the unconstrained degree of freedom, and then 3, 4, 5, 6, 7, 8. Now you are ready. Ready for what? Ready for setting up the matrix for our computation. The matrix is going to be the force is equal to the stiffness and times the displacement. This is based on the x and y axis. And the force separate into 2 types of force. One is the known force. Another one is going to be the unknown force. What is going to be the known force? The known force is going to be the force on the unconstrained degree of freedom. In this case, it's going to be Q1 and Q2. Okay, and then you're going to have the support. That is going to be the reaction. Reaction will occur as Q3, Q4, Q5, and Q6, Q7, and Q8. So the matrix is going to be larger than expected. It's going to have total of 8 members in this column matrix. So the stiffness matrix will be corresponding to that. That is going to be 8 by 8. So the stiffness matrix is going to be equal to total number of degree of freedom times the total number of degree of freedom. And again, you have this one for, let me put it in yellow, D1, D2, and then you have the what? You have the known displacement. The known displacement over here is going to be D3, D4, D5, D6, D7, and D8. So following this, you will know this force. This is going to be the applied forces. Okay, from this picture, you can see in the one direction, Q1 is going to be 0. But for the degree of freedom number 2, the Q2 going to be minus 20 kilonewton. And then you come to this one. There is the settlement of 1 millimeter. So D3 is 0, but D4 is going to be 0.001 millimeter, taking care of the settlement. And then D5, D6, D7, D8. So you will start by determining the no force and no displacement. Okay, and then you can separate this stiffness matrix by using the partition, what's so called the partition matrix. Okay, and then by this partition matrix, you may do the matrix operation to calculate, to find the unknown that we are looking for. Okay, next, just determine the what D sub k. Okay, I put this already. The D3 is 0. D4 is minus 1 millimeter because that is the settlement here. Also, D is going to be 0, but Q also have Q1 and Q2 like this. And then we got to determine the capital K matrix, which is the stiffness of the truss. Before we can find the truss global stiffness matrix, we must find the member of the truss global stiffness matrix or small k matrix here. And as we mentioned before, the small k matrix has some special character in which it can be divided into 4 portions. Let's put it in this way, okay, and then put it in this way. And you can see for a given member number 1, for example, number 1, you will have the near end here and far end here, and then actually in front of this matrix is the stiffness, is going to be the force, okay, and at the other end of it is going to be the displacement that occur in this member. It's going to be what? It's going to be Q1. It's going to be Q2. It's going to be Q3. And it's going to be Q4. XY. And then over here is going to be capital D1, capital D2, capital D3, and capital D4. But usually we don't like to put this in this kind of calculation. It's going to require a lot of work. In the actuality, we just use the notation. We know about this. It's going to be the K, and then it's going to be K1, okay, and then we just find the coordinate direction or cosine of this member. Okay, let me take this one out. What is going to be the coordinate direction cosine? Is going to be the lambda sub x, and then it's going to be the lambda sub y or dz. You have studied coordinate direction cosine since the engineering static, and that time you have the alpha, you have the beta, you have the gamma, and you have what? You have the axis of x, y, z, and then you have a vector that's putting in this direction, and then you measure the angle between the vector and the axis x. You call this one alpha, you call this one beta with the y, and gamma, that's with the z axis. Okay, and then you said you find what? You find cosine alpha, cosine beta, and cosine gamma. In this way, we use the lambda sub x by putting reference to the given axis also, but we have only x and y axis, and in this way we just said this is going to be zeta sub x, that's represent for the alpha, and this is going to be the zeta sub y. And then we define lambda sub x equal to cosine zeta sub x, and this one for the cosine zeta sub y. And before we go further, we mark this one. This is going to be the near end, and this is going to be x sub n, the coordinate of this, and this is going to be y sub n, and the coordinate here is going to be x sub f and y sub f. By putting this coordinate, you can determine this length. Okay, this length is going to be what? This length is going to be the distance of x sub f minus x sub n. Okay, this is segment. This is 0, 0. This is 3, 3. Okay, it's going to be 3 minus 0. That is going to be 3 meters. And then also you have this one for y sub f minus y sub n. Okay, and then the length of this member can be determined. The L of this is going to be L equal to square root of x sub what? F minus x sub n square plus y sub f minus y sub n square. That is going to be the length of this member. For example, this is 3 minus 0 is 3 meters, and this is 3 minus 0 is going to be 3 meters, see? And then you put into this equation, the computer will calculate it easily to be square root 3 square plus 3 square. Okay, that is going to be 2 square, 3 square root 2, okay, for the length of this. And then the definition of the cosine. For the zeta sub x, the definition of the cosine going to be this green line is going to be x sub f minus x sub n, and then divide the inclined line will be the L. And then for this one, it's going to be measured like this. You got to move this light blue into this way. Okay, to taking care of zeta sub y, and this is going to be y sub f minus y sub n divided by L. Okay, now you can determine the alpha. So, sorry, alpha is here. You got to be between the lambda sub x and lambda sub y, and then you may do the calculation. You get this one, and then you may copy this one into this one, this portion, and then you may change the side of that, and when you change the side of it, you just put this one into this portion of the matrix, okay, and then you copy it, you put it in this one. So it's going to be very easy to determine the small k matrix by following equation and procedure. Okay, take the member number one to be our first one, and for the member number one, you have the coordinate at the near end of 0, 0, and the far end of what? Minus 1.2 and plus 1.2 over here. Okay, and then you may just do the calculation. Let me put this one. If you do the computation, the height of this going to follow this one minus this one is going to be 1.2, and then the length here is going to be what? Is going to be this one minus x sub f minus this one is going to be also 1.2, and then the length is going to be 1.697, and then lambda sub x is going to be this length 1.2 minus 1.697. Okay, so lambda sub f is going to be x sub f minus 0. So it's going to be minus 1.2 minus 0 over L. Okay, you got this one to be minus 0.707. For the lambda sub y, you have the positive one. This is going to be 1.2 minus 0 divided by L. You got this positive, and I should make a note on this. Okay, if you notice the system of x and y, this is positive x, this is positive y. When you get the member putting in this direction, you can see it's going to relative to minus x. That means the lambda sub x going to be minus, and lambda sub y going to be plus. And then if you have the member in this direction following the member number 3, lambda sub x is going to be negative, lambda sub y also going to be negative. Okay, and if you notice for this member, you will know the lambda sub x is going to be minus 1, lambda sub y is going to be 0. In the opposite direction, if you put it in this direction, the lambda sub x is going to be 1, lambda sub y is going to be 0 for the x-axis. However, for the y-axis, lambda sub x is going to be 0, lambda sub y going to be equal to 1. When you do the opposite direction, okay, putting in this direction, lambda sub x is 0, lambda sub y going to be minus 1. Okay, the next we have in this direction. In this direction, plus lambda sub x and lambda sub y both plus. However, if we have in this direction, lambda sub x is plus, lambda sub y is minus. I like you guys to notice on this, to guide you how you determine it. Okay, and then you use what? This is on what I discussed before. You use the degree of freedom. When you count the degree of freedom, you count from the near end. Okay, it's going to be the tail of this arrow near end to the head of this. So it's going to be x, y, 1, 2, x, y, 3, 4. Okay, this one going to have 1, 2, 3, 4 like this. That is going to be Q, capital Q, and capital D. Going to be 1, 2, 3, 4 in this order. And then you have the AE. Okay, AE over L. Okay, no, most of the time the people like to take the AE still be here. That means this is going to be the what? The lambda sub x square divided by L. that is going to be minus 0.007 divided by, square divided by 1.697. And then the second one over here, you will have what? Minus 0. Lambda sub x 707 times 0.707 lambda sub y, and then divided by 1.697. This is going to be the second one. And then for the third one over here, okay, that is going to be the lambda sub y square. That is going to be 0.7 square divided by 1.9697. This is going to be the green one. Then you just copy the light blue, okay, from this one into this one. And then you copy the light blue, copy the yellow, copy the green, okay, and then just put into this position. You get everything for this portion, and then you just revert the sign, plus to minus, minus to plus, and then you may put it into this portion, Let's put into this portion, and then you copy it into this portion. You get the small k1, okay? And then for the number 2, the number 2 going to be next, going to be the direction in this direction, and the leg from here to here, you may not need to calculate it. You get the L of 1.2 meter without using this coordinate to compute it. It's okay. Just say it's 1.2, and lambda sub x is minus 1. Lambda sub y is 0. Okay, you don't need to do the computation since you know about it. Okay, and by this way, since lambda sub y is 0, so this one is 0. We have only lambda sub x is going to be this one. Okay, it's going to be square, and then divided by 1.2. Okay, that is going to be very easy. And then we have the near end at this point. Okay, so the order of the degree of freedom will be 1, 2, and then 5, and then 6. Okay, so we have 1, 2, and 5, 6. And then we put everything in here into our calculation, and then this is going to be 1.2 meter. Just put it over here. Okay, it's going to be 1 divided by 1.2, and then you get this one to be 0.8333, and the other members in this square gonna be 0, 0, 0. Then copy it, very easy. Then just revert the side of the member and then put it into the block, okay, the yellow block over here. Then to number 3, okay, we finish number 2, go to member number 3. In the member number 3, we have the near end at node number 1, okay, and then the far end at node number 2, and then we have the coordinate of what? 0, 0, 0 over here, and minus 1.2 and minus 0.9. This member is in quadrant number 3. So lambda sub x is minus, lambda sub y is minus, okay? And next, if you don't need to do the computation, this is 0.9, this is 1.2, the L is going to be 1.5, okay? Just put this one in 1.5, and lambda sub x is going to be what? Lambda sub x is going to be minus 1.2 over 1.5. You just put it minus 1.2 over 1.5, and then lambda sub y is minus 0.9 over 1.5. See, computation going to be very easy. and then you rearrange the number of the node 1, 2, and 7 and 8. Just put 1, 2, 7, 8, and then do the same computation. You will get this result. It's not that tough to get this kind of small k1, small k2, small k3. This is the stiffness of each member. You got to build it. You got to connect it. So you got to put small k together to get the structure or the Truss stiffness matrix. This is going to be the capital K matrix. Okay, capital K matrix gonna be 8 by 8. It's going to be the total number of degree of freedom. I have the area for you guys to put this one. I will show you for the next example. Now, for the first one, if the problem has the 1, 2, 3, 4 degree of freedom like this, your life going to be very easy. Just put every member 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. And then if you have this one, okay, it's not be like the first one, but you start with 1 and then run 1, 2, 5, 6, copy 1, 2, and then 5, and then 6, and then go to number 2 and do again. See the green one, 1, 2, 5, 6, and then go to 5. Number 5 is here. Go to 1, 2, 5, 6, and then number 6, go to over here. 1, 2, 5, 6. It's really fun to do so. Okay, 1, 2, 5, 6 for row 1, row 2, the same. Okay, and then row 5, the same, and then row 6, the same. Now we come to the K3. Let me change this one to the light blue. It's going to be row 1. We're going to be 1, 2, 7, 8. 1, 2, 7, 8, and then go to the number 2, and then again 1, 2, and then 7, 8, and then number 7. Pencil is down here. Is 1, 2, 7, 8. The last one, number 8, is over here. 1, 2, 7, 8. You can see some of the member gonna be 0. 1, 2, 7, 8. 1, 2, 7, 8. And then row 7. 1, 2, 7, 8. Row 8. 1, 2, 7, 8. Okay. The author that won't have the member, just put 0 into it, and you can see there are a number of 0 up here, over here. So it's gonna help our computation going to be easier. And then you can see some block has 3 member, but some block has no member. Some may have 2 member, some may have 1 member, and then you do the computation and note that the AE is going to be 120,000. You may put the 120,000 into this number if you prefer. Okay, but most of the time we didn't do that. And then what we have is we're going to do the partition of this. And in actuality, as we know, this is going to be the force. Okay, and then at the end of this, that is going to be the displacement. And then we separate the force into 2 types of it. One is going to be Q1, Q2. Okay, that is going to be the force 0 and minus 20, and then the reaction QT, Q4, QT, Q4, Q5, Q6, Q7, and Q8. In the other type, you're going to mark it and then do the partition. Okay, follow what you divide your force and the displacement, and then this is going to be D1 and D2. You don't know about it. When you put this, you got to do the partition of this one also. This one, D3 is 0, 5, 6, 7, 8, or 0. D4 is going to be 0.001. And you can see, you can separate it into Q sub what? Q sub K. And this one Q sub U. And then as we know on this one, this is going to be D sub U. D sub U. And this is going to be D sub K. K is known. Okay. And U is going to be the unknown. And inside this, you have what? You have the block that's partitioned into this one. And then you have this one for K11, for K12, for K21, and this one for K22. By following the matrix operation, this is known. Q sub K, okay, is going to be equal to what? K11 is going to be K11. And this K11 will time this D sub U. You just put this one as the D sub U. And then it's going to plus this one time D sub K. K12. K12 time what? Time D sub K. And then you have this one as the number, okay? And then you may just move this one Q sub K minus, okay? Minus, just put this one K12 time D sub K. See, you got to use the calculator to work on this matrix manipulation. So this is going to be the column matrix, and then it's going to be equal to K11, and then time D sub U, and then you got to find what? D sub U. You like it? D sub U is going to be K11 inverse. Okay, you got to inverse is K11 inverse, and then time the matrix that you know over here. You can find the unknown displacement for this problem. Okay, unknown displacement, and then you may use the second portion of this Q sub U. Okay, you may find the reaction. By this way, you will find the reactions by Q sub U. Just put this one up, Q sub U. Q sub U is equal to K sub 21 times this. Okay, it's going to be, this means what? You must be very careful when you calculate the D sub U, because if you get the wrong D sub U, this calculation will be wrong also. Then it's going to be plus this one time D sub K plus K sub 22, and then time the D sub K. This is going to be very simple, but it's required matrix manipulation or matrix operation. Okay, I won't allow you guys to use the software, to use the Excel, to use the spreadsheet in the examination. You guys must use your calculator, calculate only. Okay, the one that just keep calm, do not think on the calculator. I will say you are cheating. Okay, you are cheating, and then I won't grade your work, and you're going to get 0 score. Okay, but if you are at university, I will send you to the registrar to punish you if you just do nothing and then you get the answer. Okay, you must work. Okay, because that is the course learning outcome. You got to use your mathematics skill to work on this kind of course. Okay, and then you can go further. Okay, the whole operation that I put over here, put it neatly over here, and then your Q sub K equal to K11 D sub U plus K12 D sub K. And I should note in this portion K12 times D sub K. You may notice, okay, this one will time 0. This one will time this one. and the other, this one will times 0, this one will times 0, this one will times. Sometimes you don't need to put the number into your calculator. You may only use your mathematical skill. This one times 0 and this one gonna times this one. So by doing this, you may see a lot of computation occur due to the multiplication of the number and 0. Okay, so this one in short, okay, is going to be this number times this one. So I put this one to be 0.2946 times minus 0.001 and times AE times 120,000. That is going to be the first set. And the second set is minus 0.2946 times minus 0.001. Okay, the top one is going to be negative, the bottom one going to be positive, and this one will provide a forces. That forces going to be the interact with your Q sub K, which is 0 and minus 2. Okay, you just move this one, which is negative, to be plus over here. So it's going to be 0 plus that number, and then minus 20. This is going to be positive, right? And then you move it into this direction, it's going to be minus this, and this is going to be K11 times D sub U. Okay, so your D sub U going to be just the inverse of the K11 times what we have over here, and then you may put into the symbol like this. Okay, and then you may get this one, the top one. You may put all the number, you get this one, 35.355, and over here you have this one for the negative 20. Okay, and this one is positive. When you move it, this one is going to be negative 35.355. So it's going to combine into this number. See, very easy. And then you must put this one into your calculator and do the inversion. Okay, that is for the K11. Okay, and don't forget, you got to times all of this when you invert. This is going to be, actually, it's going to be K11 is going to be 1 1 divided by this one, and then the number is going to be 1.5546, 0.0254, 0.0254, and 0.5346, and this is invert. Okay, and then you will get this one. You get D1 is positive. Okay, that means it's going to move in this direction. You got this one in negative. This one gonna move downward. So you can draw the elastic curve of this truss by putting the D1, D2, and also the node over here has 1 millimeter movement. So the elastic curve of this truss is going to draw easily like this. This is a beautiful one. And then you determine the unknown displacement. Now you have this one equal to 0.204 and then 10 minus 3 or 0.204 millimeter, and this one is minus 0.872 millimeter. Okay, then you may compute for the reaction. The reaction is going to be this one times D1, D2, and then plus this one times this one. Again, on the second part, the green part, I should note to you that this one will times this one. Okay, and this one will times this one, and the other gonna be 0. Based on this, this portion going to be what? Going to be the number. The first one, this one times 0. And the second one, this one minus 0.2946. And then times minus 0.001. And then times this one, 120,000. That is the first one. And then 0, 0, 0, and then 0. The second one come into this one times 0, and this one again you got 0.2946 times what? Times this one times minus 0.001 and 120,000, and then 0 times here, 0 times here, 0 times here, and 0 times here. The author you can see the author. This one times 0, this 0 times this is going to have 0, this is going to have 0, and have 0, and have 0. You get this to be 0. Next, if you put this one, this 0 times this one, this time this one, this time this one, this time, you can see all of this is going to be 0. Okay, and then the author, let me put everything together. This is 0. This is going to be 0, and the other 0 times all the 0, you get this one for 0. And the last one, you may put the same thing, this one 0, and this one times this 0. And the other portion of this, when you times it, you get all the 0. Now, you can cross it. This is going to be very simple calculation. And again, let me put it together. You got what? You got this one for Q3, 4, Q3, Q4. Okay, only 2 of that. And then what we have is going to be Q5, Q5, Q6, Q7, and Q8. And this is going to time your K21, K21. K21 going to be here, and then this is going to be your D1, D2. See, for the computation of this block, you should put them into your calculator. If you prefer, it's going to be easier to get the result. Now you get to result, you plus them together. Okay, and then you supposed to be, don't forget about this number in front of this one. Okay, you times this one with your K21, and then times with this, and then you get the result. The meaning of the result is this: the Q3 is going to be negative, the Q4 is going to be positive, so Q3 in opposite direction, Q4 follow the D4 direction. Okay, and then Q5 is minus 20.4, and Q6 is 0. There is no force in the vertical direction here. And then Q4, and then Q5. And what you got to do is you got to check. You check what? To check the summation of x sub x equal to what? Equal to 0 or not. Okay, you may just put everything. Summation of x sub x equal to, by doing this. Let me put it into this number. It's going to be minus 2.69. Okay, this one, and this one has no value. This one 20. This one in the opposite direction, minus 20.40. And then this one plus 23.04. What did you get? You got to supposed to get the value that's close to 0. Okay, not 0 yet, but close to. This one is going to be 9, 10. Then this is going to be 23.09 and 23.04. Very close to each other. It's going to be okay. The error may occur due to our calculation use a limited number of significant figures. Okay, and then you do next for the summation of f sub y equal to what? This 2.69, and then this is going to be minus 20, this is going to be 0, and this is going to be plus 17.28. Okay, that is going to be close approximately 0. It's going to be okay, 2.69, and this one is going to be 17.28. 2.69, 17.28. That's going to be 7. Okay, and then 9, and then 9, and then 1. That is very close. Just 0.03. Okay, and then you conclude your calculation is correct. But if not, what happened? You got to do everything again. Yeah, you got to do everything again to check from the start until this point. Don't go further because there is something wrong in your calculation. Okay, now you get what? You get the displacement, you get the reaction, then you got to find the internal forces of each member. The first one, okay, you got to use this equation. Only the force that occur in the member in the far end, okay, and then following this direction, that means this one has the x palm here, and then the force that occur in the far end direction, we call this Q sub F. If this Q sub S is positive, it's going to be in tension. If it's negative, it's going to be in compression. Why? Ajahn, why don't we calculate this one? The near end, okay, the calculation is not that clear because usually the Q sub F equal to minus Q sub N. So if you know one of them, you just use it. Okay, now only this one, you have lambda sub x and lambda sub y minus lambda sub x and plus lambda sub y. You just plug this one into this equation. Beware about the sign over here. You plug this one into this equation. Beware about the sign over here. And then this is what 1, 2, 3, and 4. You have this one D4. This is D3. D3 is 0. D4, you know it. It's going to be minus 0.001, and this one is D1, this is D2, and this is D3, and this is D4. Just put the D into position and do the computation easily. Okay, most of the time I just put this one times this one plus this one times this one. This is going to be 0 plus this one times this one. I didn't put it in the matrix form in the calculator. This is going to be very easy to just put the number and time it slowly. Okay, you get the answer of 3.8 kilonewton in tension. Next, number 2. Again, this is lambda sub x equal to minus 1. Lambda sub y is going to be 0. And then the D1, D2, D5 equal to 0, D6 equal to 0. The calculation of this one going to be easier. Just this one times this number and then time it with this. You get the result. The other gonna 0. Okay, so the answer is very simple. 20.4 kilonewton in tension because it is positive. The last one. Lambda sub x is minus, lambda sub y is minus. So be careful when you put into this equation. And then this is D1, D2, and 0, 0. You get this one. Now you can do the computation easily. This one times that's one, and this one, just put them together. When you get this, just time it with this number, you get this one. The last one, you've got to check the equilibrium of this. Just cut the Truss okay, and then check the summation of x sub x must be approximately 0, and summation of x sub y also approximately equal to 0. Okay, you guys must be very careful on this. Now, there is a number of examples in the PowerPoint. Okay, on the examination, I will consider the task that subjected to the applied forces only. There is the task that subjected to the fabrication error. There is the task that subjected to the temperature change. I will put that into the examination. Okay, just put it due to the applied loading. Okay, and then I will lecture about the other example in the PowerPoint later. But for now, I think it's appropriate for me to use the writing to demonstrate you how to work on the example. So you can use this as a guideline for working on your examination. Okay, let me finish the PowerPoint here. I will come back later. And for the next one, let's us move to this one. Okay, let's us move to this one. Hello. Okay. Teacher, for the member number and node number, do you give us in the exam? I will give you in the exam sometime. But let's consider the next example. I will give you some. The author you got to consider by yourself. Okay, just let me answer you by using the next example. Okay, come over here. This one will provide you with some 5, 6, just only 2 degree of freedom number. But the author over here and over here, I didn't provide you. It is your duty to work on it. And we have some principle to work on to assign the degree of freedom. Okay, let's just consider this one, Lota. It will guide you about what you are asking me. And from this task is the examination from the previous year, and there are only 3 members. But this year I put more, maybe 5 members onto the task. But don't worry, the K1, I will provide you some information. Or if I won't provide you, the another problem supposed to be easy. Okay. Let's start by considering this task. This task is subjected to the forces. There is only 2 forces here. One is 8 kilonewton. Another one is 12 kilonewton. And then the member of the task, all the member has the same AE. This is simple. But in some cases, I may say this is 100,000. This is 120,000. This is 130,000. You must follow what the assignment that's putting into the question. You have what? You have to do the analysis by the metric displacement method. And then what we going to do again is start by considering the unknown displacement, and later you calculate to determine the reaction, and the last one you calculate to determine the internal forces. Okay, the step going to be the same as before, but before you start, you got to do the first consider the picture. You get what? You get X and Y as the global coordinate system. So the first one, global coordinate system, is okay. And then following this picture, it seems like you put this one as the node number 1. So you have the node number 2, number 3. Okay, and then you have the member number. They provide you already. And then 1, 2, and 3. Okay, let me put this 1, 2, and 3. And then you have what? You have to consider the local coordinate system. What you has over here, this is for the member number 1, this is for the member number 2, and this is for the member number 3. And I should provide you the guideline again. Just review the guideline that we mentioned before. When we have this one, we have the axis of positive x and negative x and positive y and negative y. When the member is in this direction, lambda sub x is 1, lambda sub y is 0. Okay, and then in opposite, lambda sub x is minus 1, lambda sub y is going to be 0. Now, when you go in another direction, this is lambda sub x equal to 0, lambda sub y is going to be 1. Okay, it's going to be in this direction. But for this direction, lambda sub x is 0, lambda sub y is going to be minus 1. Okay, I like you guys to recall about the coordinate direction. And then if the member putting in this direction, so this is in this direction, so you get what? You get lambda sub x positive, lambda sub y going to be positive. Okay, and in the opposite direction, you get the lambda sub x negative, lambda sub y negative. This is the third quadrant. This is the first quadrant. And then if you consider in this direction is this one is member number 3. Lambda sub x is going to be negative, lambda sub y going to be positive. That's going to guide you a little bit. Okay, when you do the computation on this. For this one, we don't have it. The lambda sub x is going to be positive, lambda sub y is going to be negative. This understanding will help you a little bit when you compute the coordinate direction, and you can compute the k, okay, easily. And the last one, we come to the degree of freedom. The degree of freedom separate into the constraint degree of freedom. Again, this is kind of a fixed degree of freedom. It occurs as the support, okay, of the structure. Another one we have is going to be the free, or what's so-called the unconstrained degree of freedom. Okay, when you consider this one, it's going to be easier to consider. This one is pin. Okay, so this is going to be the constraint degree of freedom. This is the roller. The roller in this direction. This is going to be the constraint degree of freedom. And then what are the unconstrained? Okay, so this is going to be free to move. This is going to be free to move. This is also going to be free to move. If you understand that, you may say, you may have this one as the node number 1. And you said this one is going to be node number 2. And this one going to be the node number 3. And then this one going to be node number 4. And then 5, 6 as Ajahn given to you. Okay. Lotha, this is another way to do so. Ajahn, can I put number 1 here? It's not in the order, see. You're supposed to put this on 1, 2, and then 3 here. If you put this one 1, okay, you can compute it, but the arrangement of the order going to be 1, 4, okay, 1, 4, and then 2, 3. That is no good, okay. You got to do it like this. It's going to be a lot better. So when you consider the structure and you see it has the roller here, so you must be very careful for the roller. For the pin, it's going to be easy, okay, because both degree of freedom are constrained degree of freedom, but for this one it's 1. It's going to be in a good direction. Now what we need to do is we're going to find the Q. Okay, we have two Q sub K, and then the reaction Q sub U. We are going to find what is going to be the apply forces. It's going to be apply forces, and later we will determine the reaction as asking us here, and this is going to be equal to the stiffness, capital K, the Truss global stiffness matrix. We will find the small matrix, small k matrix first, the member stiffness matrix, and then this is going to be d sub u, and this is going to be d sub k. You know this one because it related to the reaction at the support, and then you just putting this one together. Now you have the partition here into K11, K12, K21, and K22. I let you guys to see this big picture first, and then we come to finding the D sub K. Okay, the D sub K is going to be the D that related to 4, 5, 6. This problem has no detail about the settlement. That means it has zero settlement. If it has zero settlement, we have the 4. Let's put it into the black one. D4, D5, and D6, and all of them gonna be 0, 0, 0. That is going to be very simple, right? Yeah, you get some score, very simple from the picture. And then for the Q sub K, apply forces that related to the 3, 2, 1. So this is going to be Q1, Q2, and then let me put it a little bit more, Q3. Okay, just put them together. And then for the Q1, Q1 is in the positive direction, so it's going to be plus 8. Q2 is downward, it's going to be negative, okay, 12, negative 12. And Q3, no, it's going to be 0. So this is very simple for you guys to use this, right? Okay, and then most of the time, I also provide you with the required equation. Now, the next step, we got to find the K matrix, okay? To determine the K matrix, we got to consider this member, okay? Member number 1, member number 2, member number 3. We got to find the lambda sub x and the lambda sub y. To determine the lambda sub x, you got to know the coordinate. It's going to be x sub f minus x sub n, and then divided by the length. It's going to be the cosine theta sub x, and this one going to be y sub f minus y sub n divided by L. That is going to be cosine theta sub y. And then when you consider this, this can be separated into blocks like this, okay? And you guys can putting the lambda sub x squared, lambda sub y squared, lambda sub x times lambda sub y over here. Just compute only 3 of this, and then make a copy into this, and then all the block over here, you just copy it into this one, and then the other block just reverse the side of the member in the block, and then copy it over here. Okay, that is very simple. And then another equation, we talking about the equation for the internal forces. Just use the coordinate direction cosine, and then use the degree of freedom for each member. I will talking about this later. Now we come to the member stiffness. Okay, let me put this one follow what we have in the extra example. Okay, the first one, okay, we have this part. I like you guys to follow the step that's Ajahn given to you. If you cannot print this one and work on it, you got to do everything, follow what I'm given in the examination. Okay, because the procedure is going to be a kind of following the computer operation. That's why we need to follow what we have. So the first one, we have this member, okay, and then what we have is this member number 1. Some people just put this is number 1 and the direction is in this direction. That means this is the near end and this is the far end. And then you have this one for 4 and 5 and 6, and then you have this one for 3. That means what? The order of the degree of freedom will follow 5, 6, and 3, 4. Okay, 5 from x and y 6, and then the coordinate here gonna be 0, 0, following this, and then this is 0, 0. At this point, it's going to be 14, 0. Based on the global coordinate system, this is going to be 14, 0. Ajahn, I know this is going to be 14 meter. Yeah, you know it. You don't need to put it into the equation. Just follow it. Ajahn, I know this one going to be plus 1.0. It's okay. And lambda sub y is going to be 0. It's okay. Okay. If not, you just put this one 14 minus O and then divided by the 14. And this one going to be O minus O divided by 14. Okay. Or this one, you got to be the square root of 14 minus O square plus O minus O square. You're going to be a computer sometimes, but I allow you to jump to the step, jump over some step to help you working on this. Now, near end is here, okay? Far end is here. That means the degree is going to be 5, 6, and then 3, and then 4, 5, 6, and 3, and 4. Okay, follow what we previously has into this. In front of this is going near end x, near end y, far end x, far end y. Just follow this. Near end x, okay, near end y, far end x, and far end y. Just follow that, and then you may see it's going to help you just separate this into 4 box, and then you have this one as the AE. The L just gone. Okay, you may have this one for lambda sub x square divided by L. This is lambda sub x, lambda sub y divided by L. This is lambda square divided by L. This one and this one the same. You don't need to put it into the computation. So this one going to be 1 square divided by 14, or may you just put it just 1 over 14, or you may put it into the number if you prefer. Okay, and then this time to be 0. So this is 0, and this is going to give you the 0. Now it's going to be very simple. Just copy everything here, and then just put the levers in the side here, and then just put this one. Okay, it's going to be 14. Okay, and then 0, 0, 0. So the first one is going to be very simple. Now for the second one, we have for this one. This is going to be the coordinate 8. This is going to be 8 and 8, 8, 8, and this is going to be 6. I just copy this one, okay, and then we know the member of this one to be the near end, and then this is going to be 0, 0, and this is going to be the far end. It's going to be 8 and 6, okay, and actually you also know this is going to be 8 meter and this is going to be 6 meter. Okay, you may have this one square root of 8 square plus 6 square. Yes, you can do so. Or you may use this one to be 0, 0, and then this is 8, 6. So you may have this one for the square root of, okay, 8 minus 0 square plus y sub f minus y sub n, 6 minus 0 square is going to provide you the same result. It's going to be 10.0 meter. Okay, it depends on, and then lambda sub x. This one, member number 2, okay, has this direction, and then by this one, lambda sub x is going to be positive. Lambda sub y is going to be positive for sure. And then you may have the distance here, okay, it's going to be 8 meter, 8 minus 0 divided by 10, or you may say it's only 8 meter, and then divided by 10 is going to be 0.8, it's okay. And then this one going to be 6 minus 0 divided by 10, it's going to be 6 divided by 10, it's going to be 0.6, and then you have what? You have the degree of freedom number 5, degree of freedom number 6, and degree of freedom number 1, and then number 2 here. So the order is going to be 5, 6, this one, 5, 6, and then it's going to be 1, and then it's going to be 2. And on this portion, you may move this one a little bit, 5, 6, and then 1, 2. And you got to separate this one into this portion. Now, the calculation here is going to be lambda sub x squared divided by L as before. It's going to be 0.8 squared divided by 10. Okay, and this is going to be 0.064, and this is going to be 0.8 times 0.6 divided by 10. This is going to be 0.048 and 0.048, and the last one is going to be 0.6 squared divided by 10. This is going to be 0.036. Okay, if you follow this one, you just say this is 0.064, 0.048, 0.048. This is 0.036, and then put the negative into this portion and do the copy all of this number into the matrix. Okay, and then it's going to be very, very easy to do so. This is the example. It's not that hard, see. This may take you a little bit sometime with some very caution on the calculation. Now, we come to next, the member number 3. The member number 3 has this kind of direction, and then you may see this portion will has this lambda sub x as a negative, lambda sub y as the positive, and then you has this one as the near end, this one has the far end. Okay, you know this one, and you has the coordinate here of 14, 0. 14 0, and here of 8 6. Okay, and then you have this one for number 3, this one for number 1, and the degree of freedom number 2, and this is the local coordinate of this member. Now you take this one out and you can see basis upon this. You will have this one. This one is what? This one is 6 and 0. So this one is 6 meter. Okay. And if you consider in this one direction, that is going to be 8 and 14. This is also 6 meter. But following this direction, lambda sub x is going to be negative. Lambda sub y is going to be positive. Okay. The L here is going to be square root of 6 square plus 6 square. So you have this one for 6 square root 2 meter. That is the number. You may, some people say you may like to put it to be like 8 point. If you put it into the digit number, you got to use it like a 5 digit in the calculation in order to get a good estimate of this. So lambda sub x is going to be 6 minus 6 square root 2. So that is going to be minus 1 square root 2. Lambda sub y is going to be 6 minus 6 square root 2. Okay, it's going to be positive 1 square root 2. Now the number over here is going to be the minus 1 square root 2 square, and then divided by 6 square root 2. Okay, some people may get this one going to be 1 divided by 2 and times 6 square root 2. That is going to be 1 times 12 square root 2 if you prefer. Okay, that is going to be the number. Let me put it in back. Okay, 1 over 12 square root 2 for this first one. Okay, and then you got to find the other one. Lambda sub x times lambda up. This is no good. Okay, this is bad drawing. Okay, because you didn't divide it first. So, okay, let's see. This is the near end. The near end, we have this one for 3, 4, 1, 2. 3 is here. 3 is here. 4, 4. And then 1, 2, 3, 4. Okay. 1, 2. If you guide with a number, that's help you a little bit about this. Okay. And then it's going to be negative, right? Lambda sub x times lambda sub y. So this is going to be negative 1 over 12 square root 2. Negative 1 over 12 square root 2. And this is going to be positive. Lambda, this is going to be this one square. 1 over 12 square root 2. Now you copy it. 1 over 12 square root 2. 1 over 12 square root 2. And then minus 1 over 12 square root 2. Minus 1 over 12 square root 2. And then you do a copy of this. It's going to be minus, and then plus 1 over 12 square root 2. And then you make a copy 12 square root 2. 1 over 12 square root 2. 1 over 12 square root 2. And then you copy it into this. It's going to be negative, plus 1 over 12 square root 2. You just copy this one. Sometimes it's kind of bothered to do so. But just focus on what you do. Now you have 3 of the small k, and you're gonna put all of this into the structure stiffness matrix. Okay, this structure stiffness matrix have the total of 6 degrees of freedom, 1, 2, 3, and 4, 5, 6. Following this, you have 1. The reference 1, 2, 3. So you separate this one, and then you have 4, 5, 6, and over here 1, 2, 3, and 4, 5, 6 is separate into partition like this. Okay, based on the degree of freedom. Some constrained degree of freedom, another one unconstrained degree of freedom. And then you have all A sub I, A sub I, A sub I over here. So please remember, you get this 100,000 as the AE, not A sub I, AE, or the AE over here. Now, actually, the portion of this is going to be the force. Actually, let me recall you guys a little bit. This one gonna be the displacement, and then based on this, you have what? You have your D4, D5, D6 to be 0. So this is going to be 0, 0, 0. And the other going to be plus 8, minus 12, and then 0, and then separate it. And later in this portion, you get this one to be Q4, Q5, and Q6. And this is going to be the reaction. Okay, and take this one out. You get the other to be D1, D2, D3. This is going to be the unknown displacement. How you going to combine this? We do it again as before. Just put everything together. Okay, I don't have much area here, but we can do it easily. Let's go to law number 5. Law number 5, and run from 5, 6. 5 is here. Let me put it into the blue. Okay. Number 5. 5, 6, 3, 4. 5 is 1 over 4, and 6 and 3, 3, 3, 3, and then 4. Okay, so 5, 6, 3, 4. Then go to number 6. Go to and put it wrong. 5, 1 of 14. Take this one off. 0. Take this one off. Test is minus 1, 14. Okay, and number 5. 5. Let me put this one. This one 1, 14, and this one 0. This one minus. This one 0, and then for the number 6, oh, this is easy. All are 0, all are 0. Okay, and then go to number 3. Number 3 is here. Okay, number 3 start by 5 minus 1 over 14, and then 0. Okay, and then number 3. Number 3 is going to be 1 over 14, and then 0, and the last one, number 4, is going to be 0, 0, 0, and 0. Okay, that is going to be the first one. The second one, we run from 5, and then it's going to be 5, 6, 1, 2. Number 5, and then 5. Okay, over here is going to be 0.064 and plus 0.048, and number 1 is over here. That one is over here, minus 0.048. 0.064, and this one minus 0.048, and then go to 6, and then 5 is going to be 0.048 and 0.036, and then to number one over here minus 0.064, and then this one for number 2 minus 0.036, and going to number 1 run by 5 is here minus 0.064 and minus 0.0 this one 0.048, and then to the number 1 over here plus 0.064, and then 1 number 2 that is 0.048 10, then over here 5 minus 0.048, and then minus 0.036, and then go to number 1 minus 0.0 no, this is going to be plus 0.048, and then come to the 0.036, that is going to be 22. That is for the second one. And the third one you must combine them together. Run by 3 is here, and 3 4 1 2, this is going to be plus 1 over 12 square root 2 and 3, and then 4 minus 1 over 12 square root 2, and then come to number 1 here minus 1.12 square root 2, and number 2 positive 1.12 square root 2, and then come to number 4 run by 3. Number 4 run by 3 is here minus 1 over 12 square root 2, and then this is number 4 plus 1 over 12 square root 2, and then coming to 1 over 12 square root 2, and then 4 to number 2 minus 1 over 12 square root 2. Then coming to the first one over here, the first one run by 3 minus 1 over 12 square root 2, and then 4 positive 1 over 12 square root 2, and then number 1 is going to be over here 1 over 12 square root 2, and then 1 number 2, this is going to be negative, right? This is going to be negative 1 over 12 square root 2. The last one is going to be this one run by 3, this one 3 positive 1 over 12 square root 2 minus 1 over 12 square root 2, and number 1 2 and 1 minus 1 over 12 square root 2, and the last one is going to be 2 is going to be plus 1 over 12 square root 2. By doing this is require a lot of deliberation. You must be very careful, okay? And anyway, after you finish this one, you got to put them together. But before you will combine them together, let us check the K matrix must be the structural stiffness matrix must be symmetry. It's going to be the symmetric matrix. Okay, it's going to be the symmetric matrix. What it means is based on what this the member Ij will be equal to the member Ji. For example, 1 2 equal to 2 1, 3 1 equal to 1 3. Let's say by doing this one and this one. See? The same, right? Okay, that's it. And this one, this is going to be row number 1, column number 3 is going to be row number 1, column number 3 is going to be row number 3, column number 1. And then you go further. This one and this one must be the same. You don't go further until you finish checking this, because this is the very important step you guys to follow, because the symmetric matrix must be correct first before you can do so. See, you have the problem already from the red one. See, red one 1 6. Okay, you go to the red one. It's going to be 1 and 6. Okay, that is correct. And then you have to check for this one is 1, column is 1, and row is 6, column is 1, row is 6. See this one. Okay, this is not correct. You got to change it to O48 O48. This is the checking. So next, you go a little bit further. Let's see. Just check for this one. It's going to opposite to this one. And then a little bit further, this one must be the same as this one. And then this one must follow this one. And the last one, you can see they are the same. This one and this one. That is very nice. And also this one and this one are the same. Is very nice. And this one and this one the same. And the last one, this 0 and 0. That is good. And then what we have is this one and this one. And the last one that we have. Okay, you do the correction. If you check the matrix is in symmetry, that means you are in a good position. You got to put it in the next step of this. Okay, now you got to do the computation in which just taking everything. This one gonna be plus 8 minus 12 0, and then partition, and then Q4, Q5, Q6, and this is the column matrix. Just put it into the form of column matrix, and then you have what? You have equal to all of these have the AE, and the AE is going to be 100,000. Now you got to make very clear on this. Okay, I show you guys about how to calculate it. And then 1, 2, 3, 4, 5, 6 is going to be 12 centimeter. Let me put this portion into 12 centimeter and put each of them to be 2 centimeter. And what I have is this one, just combine into the square matrix. Okay, do it slowly and correctly. Please put it into the portion like this. Okay, and then for the row, okay, you just follow this one. This is going to be the displacement matrix D1, D2, D3, and separate it. And this is 0, 0, 0. Just know the displacement. And now you are going to separate this portion into partition, and then you get this. Follow what you have it before. Now you just do computation for each of this. Let's put just for the top and then copy. You just calculate this one. You get this one for 0.0 1293. And anyway, I suggest you guys to draw the line over here to make things clearer to see. Let's see, you may put something like this. This is going to be clearer. And then just put the second one. Put this one, let's say it has 0.093 and minus this one 0.0583. This is the same 0.0583. This is simple 0.064. 0.048. Okay, and then this is 0.036 and 0 and 0, and this is going to be 1, 2, 3, 4, 5, and then okay, you have this one for 0.048 and 0.036. Then you come here. It's going to be 0.09493, and this one just copy it. This one just copy it 0.5893. So the computation is not that a lot. You just need to work on it orderly. Okay, just do it slowly. It's not that hard. The third one is going to be here. That is 0.13035, and then this one minus 0.0583, and this one minus 0.07143. Okay, and then this is 0, and then this is going to be plus 0.05893, and then the last one, this is the combination 0.13543, and then the second part you just do the copy 0.01093 minus 0.05893 plus 0.05893 minus 0.064, and then you have this one for 0.48. Just copy it. This one 0.05893. Okay, and then this one minus 0.05893. This one minus 0.048. This one minus 0.036. Okay, do the computation like this, and then minus 0.05893 minus 0.07143, and then 0. Okay, and then this one 0, and then 0, and this is 0.048. You may check the computation here. With that, make sure everything okay. Just do the same. It's not that hard. Okay, and then you have what? You have what? Q sub K. This one is equal to this one K11, and then time this one time D sub U, and then plus this is K2 K11 K12, and then time this is 0, so this is gone. Okay, this is going to be simple to be K11 and then D sub U. Okay, and then you have this one to be D1 D2 D1 D2 and D3. The computation is supposed to be like this, and then you have this one. You're going to determine this one, right? So by this one, your D sub U is going to be the inverse of this one. Is K11 inverse time Q sub K. Now you get this one. okay, is going to be equal to the inverse of this. Since this has this one as the AE, so please beware about this. You got to put this one in the prospect of inverse also, and then you have this as the 0.12293 minus 0.01093 minus 0.05893, and then you just cross this, okay, and then over here you have plus 8 minus 12 and then 0 like this, and sometimes you don't need to put it like this, just copy it to be just K11 and inverse, okay. If you prefer, you may put all the member into this in order you guys to work it in order, but if you won't have time, you just skip it and put every one of this into your calculator. Now you will get this one, and then going to be divided by 100,000, and this is going to be in the unit of meter, okay, and this one going to be 116.11 minus 202.44 and plus 144.0. This is going to be divided by this one, and then this is going to be 1.161 10 minus 3 meter minus, okay, 2.024 10 minus 3, and this one will be 1.440 10 minus 3, and then you may answer this into this portion, okay, and we have this one as the D1, D2 and D3. It's going to be in millimeter. This is going to be 1.161 minus say 2.024. This is downward. This is in this direction, and this is going to be 1.440. This is in this direction, okay, it's positive, this is negative, just put it, and then you can go further to determine the Q sub U. Based upon this, you also can use this value to draw the elastic curve. Based upon this, D1 is going to be in this direction, 1.161. Okay, that is, let's say, about 5 millimeter in this direction. D1 equal to 1.161 millimeter. D2, 2.02. Okay, scaling, that's close to 1 centimeter, just downward. This is D2 equal to 2.024 millimeter, and D3, if putting in this direction, this is D3 equal to 1.44 millimeter. Now you can put this thing together and you get a new coordinate of the node, and the elastic curve of the truss can be drawn easily like this one, okay. That is going to be the elastic curve of the truss based upon the unknown displacement that we put into the position. And then, not finished yet, you may go a little bit further to compute for the Q4, Q5, Q6 now. That is going to be equal to AE. is going to be 100,000. And then you may make a copy of this. You said this is going to be k sub 2 1, and then this is going to have d1 equal to d2 equal to d3 equal to what you have over here in millimeter. Okay, but since you do this, it's going to be easier to copy this one. 116.11 minus 202.44, and this is 144.0, and they are the 1 over 10 100,000 over here, so it can be cut. And the other plus, actually this one time this one is going to be 0 0 0. Okay, and then you will get your reaction, and just go further. This is going to be easy. Just put this one into matrix times this one, and then you may get this one to be 10.286 kilonewton minus 8.0 kilonewton and plus 1.714 kilonewton. Then you need a check. Okay, you have this truss. Your truss is subjected to 12 kilonewton and 8 kilonewton in this direction. And then what you get from this reaction, you may put it into this free body diagram. Okay, the first one, the D4. D4 is over here, 10.2 nearly miss it, 286 kilonewton. And then D5 is negative, is 8 kilonewton. And then this is positive, D6, 1.714. So you check summation of x sub x must be approximately 0, and summation of f sub y also must be approximate 0. I don't have much time, so let me skip this. So you got to check it. The last one, not the last one, you got to put this one again into the reaction. That is going to be Q4, Q5, Q6, and then 10.286 kilonewton upward positive. This is going to be 8.0 in this direction and 1.714 in this direction. So just put it into this one. And the last one, internal forces, there are 3 of them. Okay, so let us work on this one. We also have the equation over here. Okay, so for the first one, we will have the Q1 equal to AE. And then if we go to the previous calculation that we have, this member has 14 meter, so 14. And then lambda sub x equal to 1, lambda sub y, lambda sub x equal to 1, lambda sub y equal to 0. Okay, so we have this one minus 1, 0, and then 1, and then 0. This is the low matrix. This one has the D5, D6, D3, D4, D5, D6, D3, D4, and then this is 0. This is 0, and D4 is 0. Only D3, you have to go back to D3 is over here. Okay, and for sure D3, not this one. This one is the also class D3. D3 is here. Okay. D3 is here. D3 is going to be this one. Okay. 114 divided by 100,000. So this is going to be 144. 144. 144 divided by 100,000, and then put this together. Okay, and then you can see this one time 0, this one time 0, this one time 0, only this one. So you have this one for 100,000 divided by 14 and time 144, and then divided by 100,000. So it's going to be 144 divided by 14. That means you're going to get this one to be 10.286 kilonewton. Okay, and then Q2 come to the second one. It's going to be this one. Okay, that is going to be 100,000, and then divided by, if you remember, this is 8, this is 6 divided by 10 meter length, and then we have 0.8 and 0.6, so minus 0.8 minus 0.6 plus 0.8, and then plus 0.6, and then the D is going to be D5, D6, and D1, D2. So D5, D6, and D1, 116.11 divided by 100,000. Another one minus D2, 202.44 divided by 100,000. Okay, you do the same computation. This one time this one 0, this one time this one 0, and this one cut this one, so you may have 116.11 divided by 10 times 0.8, and then you plus 0.6 divided by 10 times 202.44. Okay, and then you may get this one minus 2.858 kilonewton, or it's going to be 2.858 kilonewton. This one in compression, this one in tension. And then you got the Q3. We have about 3 minutes. Do again. 100,000 divided by its length. Its length going to be 6 square root 2. And then times this one. And then you go to this member. It's going to be D3, D4, D1, D2, D3, D4, D1, D2. Okay, you just put this one like this and do the computation, and minus plus. Okay, it's going to be plus minus and minus and plus 1 over square root 2. This is minus 1 over square root 2. This is minus 1 over square root 2. 1 over square root 2. Okay, you may cut this one out and put the D3. D3 144.0, and D4 is 0. This one 116.11, and this one plus D2. D2 is negative. No, it's negative. D2 is negative. Then minus 2.44. Put it into your calculator. This is going to be minus 14.546, 546 kilonewton or 14.546 kilonewton in compression like this. Okay, and then what we have is going to be node over here on the top of this is going to be the node over here. Then we have what Q1, Q2, and Q3. This is 10.286 kilonewton and it's going to be in tension, and 2.858 is going to be in compression, and 14.546 that is in compression. So take the node number 3 over here is subjected to the vertical load of 12 kilonewton if you remember it, and this one for 8 kilonewton. What we has is the member here number 3, and this one for member number 2, and Q1, Q2 is in compression, so this Q2 is in compression, 2.858 kilonewton, and if you remember this is 8, this is 4, 3, 5, and this is going to be 6611 square root 2. Q3 is upward, and we have this one 14.546 kilonewton. So please check for summation of x sub x. Okay, it's going to be approximately 0. Summation of f sub y also approximately 0. If not, you got to check it again from the start.